Good afternoon. This lecture is divided into 6 parts and the headings can be seen on the screen. I will keep the maths to a minimum, but if you want to delve deeper into the theory, then there are papers that you can download from the website shown at the bottom of the screen. So, as I see it, the world faces two major problems. The first is a lack of a viable, robust, renewable energy source, and the second is a rising global temperature. Now, I think we must all agree that the terrestrial solutions are really only making very slow progress at the moment. And so I believe attention needs to turn to space-based solutions. And these have been traditionally solar power satellites and orbiting sunshades. However, these technologies have a big problem because they require a huge reduction in the cost of access to space to make them viable. Now, I believe that mDrive offers a solution to this cost problem and will also provide power for new green transport concepts fueled by liquid hydrogen. So what is mDrive? It is a propellantless propulsion technology, and it's been developed over the last 20 years with UK and US government funding. It's also been developed in China and Russia, but it is shrouded in secrecy and a little public controversy. This is really quite understandable. I mean, the military applications of mDrive are quite scary, and it is really only the defence organisations that have the money and the capability to carry out these rather difficult R&D projects. So if you look at the two diagrams which compare mDrive with a conventional rocket, you can see that both really produce a force in one direction and an acceleration in the opposite direction. mDrive is not a reactionless thruster. I mean, such things don't exist. It is simply a new class of electrical machine. It's a machine that produces a linear force, which we call thrust, and is subject to an opposite reaction force or an acceleration. There's no new physics, no alien technology or magic. And as with all machines, mDrive obeys the law of conservation of momentum and the law of conservation of energy. So to answer the question that was put up on the flyer for this lecture, yes, mDrive really can produce thrust without propellant. But to understand how, you really do need to understand the basic physics. But first of all, let me tell you where mDrive came from. We need to go back to the 1970s, and the Cold War was at its depth, was driving missile technology very rapidly. In the UK, we had a nuclear warhead program called Cheveline, and it was suffering from problems in the propulsion system. Now, in his 1974 Royal Institution lecture, Professor Eric Laithwaite has suggested that gyroscopes could provide a means of reactionless propulsion. This was a little controversial, but the MOD picked up on it, and Sperry Gyroscope, for whom I worked, they were an American company. They were asked to investigate, and Sperry Gyroscope were the experts in gyroscopes. So I joined a team that was tasked with to think the unthinkable, and that's a really exciting thing for a bunch of young engineers to be asked to do. Well, we worked through it and concluded that a mechanical system really could not provide such a propulsion system. but an electromagnetic one would, but with very low thrust. At this time, we first realised that reactionless propulsion was actually impossible. Propellantless propulsion is quite feasible. Now, key to a lot of this work on the electromagnetic side was a paper written by Professor Alex Cullen of UCL. He'd written this back in the 1950s, but it really was key to the work that we were doing. Well, we all moved off, did our own things, and but in the 1990s, the concept was resurrected as part of Project Greenglow and became M-Drive. So let's look at the science behind M-Drive. High frequency electrical energy at microwave frequencies is directly converted to thrust by the forces caused by the radiation pressure on the end plates of a cavity. Now, the cavity is a resonant cavity, and the group velocities at each end are significantly different. Therefore, at the large end, the group velocity is approaching the speed of light, whereas at the small end, it's approaching zero. It is in fact approaching what we call the cutoff condition for a waveguide. Now, because the group velocities at each end are very different, the forces at each end plate will also be very different. Thus, F1 is very much larger than F2, and the difference between these two forces, F1 minus F2, is what we call thrust. So let's look at some of the basic physics in a bit more detail, particularly radiation pressure. It's not really pressure, but it is simply the force that is produced by the same process as that in any other electrical machine. The faster the magnetic field cuts the end plates, which is the conducting element, the higher the induced current in that conductor and the higher the force. This is sort of standard electrical engineering, but Cullen in his paper derived radiation pressure from F equals BLI, which is the standard machine equation, where force equals magnetic flux density times the length of the conductor times the current induced in that conductor. However, in M-Drive, the magnetic field is actually a radiating field rather than the induced field that you find in most electrical machines. And as such, you can't really model it as a standing wave. This will always give you a zero total force in any shaped cavity. Indeed, if you model it as a standard finite element software package, this assumes a standing wave and you'll get zero. It gives you a nice picture of the field pattern, but zero force. So the other thing you must understand is that the force from this radiated field is a maximum when the surface is orthogonal to the velocity vector, and zero for a surface parallel to the velocity vector. And this is why the two end plate forces are not cancelled out by the sidewall forces. In a properly designed cavity, the sidewall forces are negligible. As well, the world inside the cavity obeys Einstein's principles, and therefore the electromagnetic wave is actually independent of the cavity, and this independence of velocities means that M-Drive is an open system. The world outside the cavity, though, obeys Newton's laws, and therefore thrust that's produced by the cavity is opposed by a reaction force or an acceleration in the opposite direction. Now, in both worlds, the law of conservation of energy has to be conserved, and actually mDrive can operate as either a motor or a generator. Well, now we need to look at a rather more difficult part of the theory. If you look at the simple diagram at the top of the slide, you can see that we say the cavity produces the force thrust T, and it accelerates in the opposite direction with an acceleration A. Now, as it's accelerating, the cavity will build up kinetic energy, EK. But because it is a resonant device, it already will contain stored energy, ES. And this stored energy is built up under a time constant, Tc. Okay, let's take the first situation where the load that you apply, load being a force which you apply to the cavity, is greater than the thrust. In this situation, obviously, the cavity will not accelerate, but there will be a reaction force R in the direction of acceleration. This will directly oppose the force, which we call thrust T, and therefore you will get no force, resultant force on the cavity, and no force will be measured. This is simply the fact that T plus R equals 0 and momentum is conserved. Under acceleration, however, the momentum gained by the cavity is balanced by the momentum lost by the electromagnetic wave during the time constant Tc, and that's an important point. If we look at the other extreme, where there is a zero load on the cavity, then things are more complicated because you have to consider the derivatives of kinetic energy and stored energy. To put it simply, if the rate of change of kinetic energy is greater than the rate of change of stored energy, you will never build up stored energy in the cavity, you will get no thrust, no constant force will be measured, but energy will be conserved. So this means that thrust or reaction force can only really be measured when the load is between 0 and T. Now, this has an important point when in orbit, because in that condition the load can equal 0, and various techniques are used to overcome this condition. Pulsed microwave inputs, such as occurs in third generation mDrive, or indeed a mechanical pulse, can be used to solve this zero load problem. Now, mathematically, experimentally and operationally, there is evidence to support this rather more complex thrust against load theory. Now, the equation for static thrust is quite easily derived from, I guess, the two most famous equations in physics, F equals ma and E equals mc squared, thanks to Newton and Einstein. Dr. Bailey of the Royal Radar Establishment at Malvern, who was a former pupil of Cullen, showed that radiation pressure can be greatly increased by the use of a resonant cavity, and this was back in 1955. And therefore, when we look at the resultant thrust from an mDrive cavity, we can multiply the standard 2p over c equation for radiation pressure by the Q factor of the cavity. Now, the other factor that's used, dF, which is a design factor, is dependent on the relative sizes of the large end plate and small end plate. But if we look at the effect of Q, you can see that at room temperature you would have Q of about 50,000, 5 by 10 to the fourth. But if you go to a superconducting cavity using, for instance, IBCO, which is a so-called high temperature superconducting material, it's yttrium, barium, copper oxide. And if you cool it to liquid nitrogen temperatures, you'll get a Q of about 5 by 10 to the sixth. If you decrease the temperature by using liquid hydrogen, you can get 5 by 10 to the eighth Q values. And for a niobium cavity cooled with liquid helium, you can go right up to 5 by 10 to the ninth. And liquid helium cooled niobium cavities are actually used in the accelerators for high energy physics research. And indeed, when they pulse these with high power microwave pulses, the cavities actually stretch under the forces, which can approach several tons. The serious development of mDrive really began around 2001. We were funded by the UK government, and technical monitoring was carried out by DSTL at Farnborough. In fact, our technical monitor was the late David Fern, who some of you will recognise as the father of UK electric propulsion. Okay, we started off with an experimental thruster, a fairly low Q of 5.9 by 10 to the 3, and thus a low specific thrust of about 19 millinewtons per kilowatt. It was powered by a simple commercial magnetron, but what this early thruster did was to show that we could either eliminate or calibrate out all the spurious forces that were suggested to us that could be the cause of our measurements. So that was a fairly important initial set of tests. We then moved on to a demonstrator engine, and by 2006 this engine was actually rotating on an air bearing and demonstrating Newton's laws. Again, it was powered by a magnetron, at this time a water-cooled high power device. We then moved into two parallel programs. The first was our experimental superconducting thruster, built as a rectangular cavity using IBCO thin film on sapphire substrates. A difficult and rather fragile setup, which worked pretty well to begin with, but then the thin films, or rather the substrates, cracked as soon as significant forces were brought to bear. The flight thruster, however, which was run as a parallel program and at the same frequency of 3.8 gigahertz, was developed and eventually transferred to America under what's called a TAA, which is a Technology Assistance Agreement, which was set up between the UK government and the US State Department. Now, it's interesting to note that both the flight and superconducting thrusters used narrowband inputs from a travelling wave tube amplifier. And this was quite a step forward, because not only did it give you much more precision over frequency control, but it did mean that the thrusters, the cavities, required a lot more precise machining. Now, the data that you see in this graph is collected from a number of sources and is now quite out of date. It's up to 2015, but you can see that the experimental data shown as the dots all cluster around a straight line, which is the predicted specific thrust against Q, assuming a design factor of 0.6. Interestingly, the one outlier is the Kenai superconducting cavity from America. Now, there's a lot of data on the both the theory and the experiment, so you can download again from our website. Now, during the development work here, as always, you come across, and we came across, some significant engineering challenges. Now, microwave cavities are difficult. Uh, the first time I came across one was actually on the ESA Olympus satellite program, and there, because of an incorrect cavity design, for the first 8 years of the program, the comms payload was being referenced by a rather unstable local oscillator. We sorted it in the end, and it was launched in 1989. But that was really only a small, fairly low Q symmetrical cavity. Now, M-drive cavities are high Q and they're asymmetric, and so they are extremely difficult to engineer. A good example, for instance, is the machining tolerance, is where if you've got a Q of 50,000 and a 1 micron error, your total path length over the time constant can be as high as 50 millimeters, which is actually approximately equivalent to half a wavelength. Also, the end plate alignment is very critical. A thousandth of a degree alignment error, and the eventual total path, completely misses the end plate and bounces off the side walls. So, you know, there is a lot of precision and care needed when you machine a cavity. If you look at the problems around the inputting the power into a cavity, which was essentially the problem on the Olympus satellite. It doesn't matter whether you use a slot, a loop, or a probe. It has to be tuned to the resonant frequency and must match the wave impedancy at the actual input position that the circuit is. As you go down the cavity axial length, then the wave impedance varies quite significantly as the guide wavelength varies. And indeed, as the guide velocity varies. Also, under high power operation, the input elements in the cavity have very different thermal responses, and this can lead to quite difficult real-time tuning as you power these things up. The other thing, of course, is that with high Q and high power, you have very large field strengths within the cavity, and you have to be carefully designed so that you don't cause any breakdown, and they are inherently dangerous, M-drive thrusters, when they're working properly. The final thing is that when you test these devices, you have to take account of basic physics, and as we've mentioned, you have to understand the loading effects on the test equipment. So M-drive has been developed really over 3 generations, and the first generation is a simple uncooled microwave cavity, relatively low specific thrust, but ideal for in-orbit space applications, typically with a specific thrust of around 0.3 newtons per kilowatt, although there have been reports of quite significantly higher specific thrusts. Second generation are thrusters that have simply been manufactured using superconducting cavities and are cooled, for instance, by liquid hydrogen. Now, these have significant problems with acceleration. Under any significant acceleration, the Doppler shifts inside the cavity destroy the Q. but they do have a very specific application for very large marine vessels. So supertankers and bulk carriers are quite good using second generation cavities. The real breakthrough was when we worked out how to cope with the Doppler problem, and this led to the third generation cavities, typically cooled by liquid hydrogen. They give quite a high specific thrust, and you can actually get some reasonable accelerations out of them. Although, of course, the acceleration is still limited by the conservation of energy. And here we're talking about space launches and a very exciting moon mission. We're talking here now up specific thrusts of almost 4 kilonewtons per kilowatt, so sort of half a ton per kilowatt. Now, the fourth generation is very interesting in that if we were able to employ room temperature superconductivity, then we would get not only high performance propulsion systems, but quite lightweight vehicles, because you wouldn't need the large amount of liquid hydrogen to cool the superconducting cavities. Room temperature superconductors that are suitable for M-Drive are not actually in the public domain, but US research is actually ongoing. So now we'll look at the applications of M-Drive, and we'll start off with first generation. And I mentioned that typically you can get about 0.3 of a newton per kilowatt out of a first generation thruster. Well, for this particular design, we've increased that to 0.5 of a newton per kilowatt, essentially by using radiative cooling, and you can see the sun shield that we would deploy. Also, the cavity is much smaller than the flight cavity because it uses a T113 mode, and for this particular design, you can get to Mars a single trip in 76 days. If you're prepared to spend 1.4 years in constant acceleration within 1 AU of the Sun, then you can spiral out to deep space and reach Pluto in 2.64 years. So for space science community, the M-Drive offers the chance for the whole of the solar system to become your backyard, which is rather exciting, I feel. Now, the original commercial application for first generation M-Drive was to provide primary and secondary propulsion for a communication satellite in geostationary orbit. Use of M-Drive would effectively halve the cost of the launch and double the operational lifetime. So if we take the 3-ton satellite shown in the picture there, it would typically contain 1.7 tons of propellant. You get rid of the propellant and you'll halve the mass of the satellite. You would then do a conventional launch to low Earth orbit, where you deploy your solar arrays and antennas, and then spiral out to geostationary orbit in about 36 days. There, the station keeping and attitude control would be by smaller M-Drive thrusters, and of course your operational life is no longer restricted by your propellant reserves. Now, this concept wasn't actually very popular with satellite and launcher manufacturers for obvious commercial reasons. A particularly interesting second generation application, where we're now using superconducting thrusters but without any Doppler correction, was when we looked at the propulsion system of a supertanker. This was done as part of a study with the Shell company. And we used a 555,000 ton tanker as an example, and we improved the specific thrust of the vessel from a typical 0.13 kilonewton per kilowatt electrical for conventional propulsion. We improved that to about 0.4 kilonewton per kilowatt using an M-drive thruster. Which is a pretty good improvement. This was actually using a fully closed cycle cooling system, which wasn't really very efficient. So when we looked at the use of M-drive propulsion for a liquid natural gas tanker, we found that rather we could actually make use of the natural boil-off of the payload to provide both cooling and electrical power. So in effect, you could do your full voyage without any use of any fuel at all. This was realized by Shell that it would have a disastrous effect on their marine fuel market. They took fright and withdrew the funding. That was sort of unfortunate, because later on it was suggested to us that there are about 60,000 deaths per year due to the pollution from heavy marine fuel. So that would have been a very useful development had it carried on. Another application we looked at for second generation M-drive was long-haul air transport. This was back in about 2013, and our concept then was a hybrid spaceplane, where M-drive would be used for the lift engines, and horizontal acceleration was given by a combination of rocket and jet engines. Now, flying at about 100 kilometers altitude, this would get you from London to Sydney in about 2 hours 40 minutes, compared to the current 19 hours. It would be city centre to city centre with quiet vertical takeoff and landing, and you'd be using liquid hydrogen fuel, so there was no pollution. We would typically carry 100 passengers, and the cost per passenger mile was well below the current British Airways costs. So this was a pretty interesting concept, but when we moved on to the third generation M-drive, we were able to much improve the performance for this sort of application. So we'll now have a look at a third generation thruster. This is designed to overcome the acceleration limitations that you get due to the Doppler shift in a very high Q superconducting cavity. This particular one operates at 950 megahertz, so it's quite a big one, and it operates in T211 mode. We use circular polarization to enable a measurement of the instantaneous Doppler shift, which is then used to correct the frequency at the input, and is also used to compensate the path length in real time. The path length compensation is carried out using piezoelectric elements, which are also actually used for real-time control of the end plate alignment. We used pulse modulation because you can't keep continuously extending the path length to overcome the Doppler shift, and because it's pulsed, we would use two cavities operating in line to allow reset to occur. This would give us a relatively constant thrust with just a small ripple on the top. We also used pulse modulation to compensate for changing of the load conditions, and this was particularly highlighted by a study we did for a manned moon mission. The requirements were to land 3 astronauts on the moon, bring them back again, and give them a benign flight environment suitable for space tourism. Interestingly, an M-drive propelled vehicle, because it is only subject to low acceleration and thus low mechanical and thermal stresses, can actually be constructed by a car manufacturer, particularly one who has hydrogen-powered fuel cell technology. And the efficiencies involved, if you look at the difference in scale between the Saturn V and the personal space vehicle, you can see that the advantages are enormous, and therefore everything is going to change in the launcher and aircraft business, and it certainly opens up scope for new industries to come into this business. If you look at the Saturn V, which you needed to get 3 men to the moon and back, 110 meters high, 3,000 tons. Look at the small personal space vehicle, which will do exactly the same, 6 meters high, just over 10 tons. I mean, the difference is actually quite staggering. Now, if you look to get large payloads into orbit, then you need a heavy launch vehicle, and this concept has been with us right from the beginning. It was originally described by a US Air Force officer as being like a space elevator without the cables. It simply takes large amounts of payload into orbit, slowly, quietly, no fuss. In fact, we were looking for 50 tons to geostationary orbit. It needed to be fully reusable, and 500 missions were suggested as an operational life. The idea was that you hung the payload underneath the wing. It had vertical takeoff and landing, but also had glide capability. And in particular, it was highly maneuverable because you needed the vehicle to actually carry out the payload docking, and indeed perhaps some deployment of the payload. So you needed pitch, roll, and yaw, but also X, Y, and Z translation, and this was achieved using 4 fixed lift engines and 4 gimbaled engines with 2-axis gimbaling. It also gave you high levels of engine redundancy. You can see we did quite a bit of work on this in the early days, and it even went to the extent of doing aerodynamic tests on a 2-meter scale model of it, which was great fun. It did fly, but obviously powered by air turbines, not M-drive engines. The launch vehicle sort of progressed through a number of designs, and this is an outline sketch of what is effectively our latest proposal. You can see the 8 M-drive engines are all set in what's called a thrust frame with a large liquid hydrogen tank on top, and the payloads hanging underneath. It's a very simple structural concept, giving an overall length of about 29 meters and a wingspan of about 20 meters. The total launch mass is really quite low at 116 tons, and that includes 15 tons of liquid hydrogen. It goes very slowly up to orbit. It takes 6 hours with a mean acceleration of 0.014 g, very gentle. In fact, the maximum velocity through the atmosphere is only 70 miles an hour. And of course, this vehicle is unmanned, fully remotely controlled, or under AI control. The key to solving our current global problems is seen to be solar power satellites, and this was recognised back in 2011 by a major report which clearly stated there were no technical barriers to solar power satellites, but there was a very large question over the economic viability. And the most critical part of the economics of solar power satellites is the cost of getting it from Earth to orbit. You can see the problem. This particular modular Sandwich microwave solar power satellite from 2011, which was the best that they could do at the time, gave a total mass of 6,700 tons. This was to achieve an output of 2 gigawatts, which is typical of a terrestrial power station. If you were to use Atlas rockets, the sort of biggest ones around, you'd need 1,700 of them to get all this kit into orbit, at a cost something like $194 billion. And this is to be compared with the $20 billion which the study requirement gave as a maximum cost to make the thing viable. So clearly there's a 10 to 1 cost disadvantage at the moment. So we took on the challenge and looked at what a heavy launch vehicle would give us, and the costs came out at about $1.5 billion. So huge cost advantage, well below the study requirement, and indeed well below the cost of a standard nuclear power station. I mean, the thing's a no-brainer, really. We reckoned it'd need 134 launches. If you had a fleet of 3 heavy launch vehicles, it would take a year to build. And you'd also use the launch vehicle for all the docking and deployment functions. Now, if you can put these very large solar power satellites into geostationary orbit, you can put sunshades into the Sun-Earth L1 point with similar cost savings. And there you can start to provide a bit of shade for the Earth. You can also combine them with the power satellite function. You would then need to use laser power transmission back to geostationary orbit, and then the standard microwave transmission from geo to Earth. The big thing about these orbital sunshades is that they would be completely controllable. You would use first generation thrusters, M-drive thrusters for the AOCS, that's it, the attitude and orbit control functions. And you would be able to control these sunshades or the attitude of these sunshades in real time. So you could modify the amount of shading you needed at any given time. One can imagine that there are many cities around the world that would probably pay a high price for a few hours of shade every day, and of course shading at the poles would be enormously useful in cutting down the problems of global warming. So let's now look at what room temperature superconductivity can do in fourth generation M-drive and how it will be applied. And certainly electrically powered air taxis are being developed in many countries, but we need to look really at the future of this sort of vehicle. And the personal air vehicles, the M-drive personal air vehicles, will still be using battery power or fuel cells as the existing air taxis, but they will be a lot more viable because they can go anywhere without causing problems by large propellers and by shifting large amounts of air downwards, which is pretty disruptive. With room temperature superconductivity, we no longer need the large tanks of liquid hydrogen, and the whole vehicle can be constructed with absolutely no moving parts. It'll all be pretty well solid state. It'll be fully automatic, probably under voice control. And it's envisaged that the actual airframe could be built from high-tech glass, which is actually under development at a large glass manufacturer already. And interestingly, it's proposed that the operational life of these vehicles should start to be specified in centuries rather than a few years. Quite a significant improvement. For those of you in the space industry, you'll recognise the term FMECA, F-M-E-C-A. It actually stands for Failure Modes, Effects and Criticality Analysis. And if this is done for the human race, particularly if it's done over a number of generations, the probability of mission failure is very high. In fact, it becomes inevitable, and for the human race, mission failure is potentially extinction. So what we need to do really is to build into our system a bit of redundancy, and the aerial refuge community, the ARC that you see here, is just such a redundant feature. In this proposal, you have a very large structure, 1.6 kilometers in diameter. We're housing 7,000 people, and totally powered through the solar power satellites that we envisage being in orbit by then. And you can see that the geodesic dome roof is ideal to act as a rectenna for the microwave power beams from the satellite. The lift for the whole structure will actually come from air temperature differences. You've got 7,000 people in there, and they generate a lot of heat. But the whole structure, it's a flying vehicle, so it needs to be stabilized and propelled. And this is where fourth generation M-drive thrusters will come in. If we look at the internal view of an arc, we can see that, that there's some work already been done. The homes are lightweight, single-story courtyard designs. The whole community is self-sufficient in food. It's proposed they would actually farm using a soilless aeroponic system. And of course, this farming requires quite a lot of energy, but of course you have a fully resilient power supply available, so it becomes a very viable way of living. But it does need to be worked on, and the architecture for these arcs really needs to begin on Earth now, I think, so that we are not rushed into producing these things as an existential crisis dawns on us. So it's this sort of thinking that makes M-drive essentially a technology of hope. You know, there is hope for the world. We shouldn't be all doom and gloom at the moment. But we do need to look at how M-drive will develop to provide this technology of hope. And it will, as all technologies, will be driven by what people want, what the customers want. And we can see that first generation M-drive will clearly improve satellite performance. But it is the second and third generation M-drive that will give the major shifts forward. It will, in fact, be a paradigm shift in terms of energy and transport applications. And the big step forward will be for solar power satellites, getting those into orbit. I mean, it is acknowledged and has been acknowledged for some time that really the solar power satellites are the best solution if you're looking to produce a green baseload energy source. But you do need to reduce the launch costs. And of course, we need to move away from carbon-based fuels for future transport. And here, hydrogen again is acknowledged as the best solution. But you've got to produce it, and to produce it, you need power, and you need green, sustainable power. So you've got solar satellites. Once you're using the power to produce large quantities of hydrogen, you can use them to feed the fuel cells and M-drive engines in all forms of transport. We've seen that it's an enabling technology, if you like, for even more ambitious space missions, where we're looking to get involved in geoengineering, as it's called, but it needs to be controlled geoengineering. So some of the proposed solutions are pretty scary, but we need to be in total control if we're going to start shading the Earth. And of course, we've seen future applications of the room temperature superconducting versions of M-drive, and a very interesting and potentially life-saving application of these airborne refuges. However, we must acknowledge that M-drive is a highly disruptive technology. it does sort of face and has faced severe opposition from vested interests. But we must persevere because it is the one way to move into a truly sustainable world. In some ways, we need to, if you like, change the sword of mDrive into a ploughshare or a number of ploughshares. And I'd like to leave you with a last thought that at the moment mDrive is a bit like an iceberg. Most of the knowledge, unfortunately, is out of sight, and a long career in the defence industry tells me this knowledge is not actually going to be given up very easily. So it's you guys who need to start asking the questions, learning the science, and pushing the people who know to explain. And you need to start to do this soon before the real icebergs start to melt. Thank you.